Hey Timmy, I've been hearing a lot about these magnetic levitation trains, or maglev trains, lately. Can you explain how they work, both in terms of levitation and propulsion? It's truly fascinating.
Absolutely, Ethan. Maglev trains are a remarkable blend of magnetism and engineering. Let's dive into the dual aspects of levitation and propulsion. First, let's start with levitation. Magnets have two poles, the North Pole and the South Pole. Additionally, each magnet has magnetic fields, and when two magnetic fields interact, various results can happen. Similar poles of two magnets repel each other, while opposite poles attract. This basic principle of magnetism serves as the foundation for maglev technology.
Right, I remember that. How does it relate to the levitation of maglev trains?
Excellent question, Ethan. In maglev trains, powerful electromagnets are utilized to levitate the train using the same aforementioned forces. These electromagnets are created by passing an electric current through a wire, generating a magnetic field around the wire.
Can you explain a little more about electromagnets and how they work?
Sure, electromagnetism is the interaction between electric and magnetic fields. Electric fields are created by electric charges, either positive or negative, while magnetic fields are generated by moving charges.
So when electric charges move in the wire, magnetic fields are created?
Excellent. According to Ampere's law, the strength of the magnetic field around a wire is directly proportional to the electric current flowing through the wire. The equation shows this. In this equation, B represents the magnetic field strength, mu is the permeability of free space, I is the electric current flowing through the wire, and R is the distance from the wire.
That's fascinating. So by manipulating the current in the electromagnets, we can control the strength of the magnetic field and, consequently, the levitation of the train. I'm pretty sure there's an equation that helps us understand how a magnetic field is directly proportional to the force exerted on magnets. Lorentz force law, F equals I L B sine theta, shows that F and B are directly proportional. So the greater magnetic field and the greater the current in electromagnets, the greater the force exerted on the train, and the higher it will levitate.
On the train, there are electromagnets facing downward, and on the track, there are arrays of permanent magnets facing upward. When the train's electromagnets are energized, they create a magnetic field that repels the magnetic field of the track.
So the repulsion between the train and the track helps the train levitate?
Exactly. This repulsive force lifts the train slightly off the ground, creating a cushion of air. It's similar to how two magnets with like poles facing each other repel and float above one another.
Isn't it dangerous for the passengers to have the train completely hovering?
By controlling the strength of the electromagnets, the train's height above the track can be adjusted, allowing for stable levitation. This usually means levitating just a centimeter above the track.
That's amazing. So the train floats without any physical contact with the track.
Precisely. The absence of physical contact reduces friction, resulting in smoother and more efficient movement. While regular trains can reach up to speeds of 124 miles per hour, maglev trains easily reach up to 311 miles per hour. Friction really does have a large effect on trains. Now, let's move on to propulsion. The propulsion system of maglev trains is achieved through electromagnetic propulsion. It involves the interaction between the train's magnets and the magnetic fields generated by the track. On the train, there are electromagnets facing forward. These electromagnets are controlled by a computer system and can be rapidly switched on and off.
How does the interaction between the train's electromagnets and the track's magnetic fields propel the train forward?
Great question. As the train's electromagnets are switched on, they create a magnetic field. This magnetic field interacts with the magnetic fields generated by the track, which is a combination of permanent magnets and electromagnets. Depending on the polarity and timing of the electromagnets, this interaction produces attractive or repulsive forces. propelling the train forward.
So, by manipulating the electromagnetic forces, the train is pushed or pulled along the track?
Exactly. By precisely controlling the activation and timing of the electromagnets, the train can achieve continuous propulsion. This allows for efficient movement and high-speed travel. The magnets on the train and track are positioned in a way so that the train has a net force in the direction it wants to accelerate. These forces help propel the train forward while the train remains floating and cause negative acceleration, slowing the train down.
Right, so two magnets are lined up, and one on the train. One in front pulling the train with the opposite magnetic pull, one in the back repelling with the same magnetic pulls. The net force would be forward, so the train would accelerate forward. This can be altered through electromagnets, whose charge and magnetic field can be changed, and the train can move forward and backward.
The combination of magnetic levitation and electromagnetic propulsion makes maglev trains a revolutionary mode of transportation, offering smooth, energy-efficient, and high-speed travel possibilities.
It's incredible how magnetism and precise engineering work together to create such advanced technology.
Absolutely, Ethan. The application of magnetism in maglev trains showcases the boundless potential of science and engineering.
I've heard about a thing called SC maglevs, which are faster and better than regular maglevs. Can you explain what makes it so unique?
Sure, SC maglevs are superconducting maglev. What makes these trains different from regular maglevs is the use of superconducting materials, which are able to conduct electricity with zero electrical resistance when cooled to extremely low temperatures. Electrical resistance is the opposition of current flow in an electric circuit, which is used in maglev technology for electromagnets and the train's propulsion.
So when a material is cooled down enough, superconductivity will occur, and high electric currents will be carried without much opposition, right?
Certain alloys, such as liquid nitrogen or helium, are cooled to temperatures below negative 200 Celsius.
You know, I also heard that they're good for the environment as well. Is this true?
Yes, they require 30 to 50% less energy than regular maglevs because of the lack of electrical resistance, making them one of the most efficient modes of transportation. They are also low maintenance because there is no contact between parts. However, their construction is a grand infrastructure undertaking, as it requires dedicated tracks and specialized cooling systems.
Maybe they'll be the future of transportation, and we'll be riding on maglevs instead of subways.
That's a possibility. Superconducting maglevs offer incredible speeds, efficiency, and safety, and they could revolutionize the way we live our lives.